Hi, I'm Eric, and today we'll be continuing to learn number theory. Now, last time we learned congruences, powers, and Fermat's little theorem. Now we are going to learn congruences, powers, and Euler's formula. Euler's formula, sorry. Now, these two words are basically the same, and Euler's formula is basically the formula he got after he looked at Fermat's little theorem. Now, Euler looked at Fermat's little theorem and found one of the things that you need in order to say that Fermat's little theorem is true is that P is a prime. Now, after Euler saw that, he was like, can we make P any number, not just a prime number? And so he went on his voyage in finding Euler's formula. So first things first, we've got to introduce a new character, and he is phi. Well, what is phi? A Greek letter pronounced F-H-I. Oh my gosh. P-H-I. Phi. Now, phi m is basically the number of integers between 1 and m that are relatively prime to m. Now, let's take an example, 10. Well, 1 is certainly one of these numbers. Is 2 okay? No. 3 is okay. 4, 5, 6 are all not okay, but 7 and 9 are. So phi 10 is equal to 4. Now, it seems like this is a complete random list, but we find that when m is a prime, phi m is basically m minus 1. 2 is 1, 3 is 2, 5 is 4, 7 is 6. And that is quite obvious because the definition of primes is that they only have two factors, 1 and themselves. So they must have m minus 1 for phi m. And we can write it as this because we'll use p for prime, not just m. Now, he got this and he went like, Fermat's theorem, it includes x to the nth power. So I've got to include that too, or else it won't be the same. So he gave himself an example. Well, it's actually we gave ourselves an example to understand how he came up with the formula. So let's say we want to know 7 to what power is congruent to 1 modulo p. Actually, it actually should be modulo m, because that's our purpose. Now, actually, we won't have an m here, because then it will be like one real number and one variable. So we'll set m to 10. And notice that phi m, I'm obsessed with m today, phi 10, it's actually 4. And you'll see why this actually gives us a very unexpected rule later on after we solve this. So now how are you going to solve this? Well, we find all of the numbers that are relatively prime to 10 inside 1 and 10. And these four numbers are, I'm going to write it in yellow, 1, 3, 7, and 9. These four numbers. Now, if we multiply them all by 7, we actually get a surprising result. Now, I won't write the modulo 10 because it takes up too much space and time. So we'll just write 7 times 1 is congruent to 7 modulo 10. 7 times 3 21 is modulo to 1. Is congruent to 1 modulo 10. 7 times 3, oh my gosh, I'm stuck in an infinite loop. 7 times 7 is congruent to 9 modulo 10, and 7 times 9 is congruent to 3 modulo 10. Now notice that it's 1379 in this list, and if we rearrange these four numbers, we also have 1, 3, 7, and 9. So we find a similar pattern to when we tried to give ourselves an example to understand how Fermat came with his little theorem. And now we'll do the exact same thing from last lesson. Oops, doopsie. Well, what was that thing? Oh yes, it was like multiplying these four terms together. 7 times 9. Oops. It's congruent to 1 times 3 times 7 times 9. And if we get out the 7, and we know that 1 times 7 times 7 times 1 times 3 times 7 times 9 is relatively prime to 10. So we can divide both sides by 1 times 3 times 7 times 9 once we get out 4 7s. So we have this modulo 10. And it's to the fourth power, and we have solved that. Not only that, but I said this would come in handy, and it did. Look, 4. They're the same. So Euler came up with his formula, which was like this. If A and M are relatively prime, we can't cancel that. We can't cancel that fact. Then A to the phi m's power is congruent to 1 modulo P. Modulo M. Now, this is actually very easy to prove, since we had proved Fermat's little theorem. And Euler's formula, it's like a little brother to Fermat's little theorem. So it's basically the same proof, just with different numbers. So the set of B's will be phi m, which is the numbers between 0 and m that are relatively prime to m. Now when we say 0 to m, it will be not inclusive, but if we say 1 and m minus 1, it will be inclusive. So then, if a and m are relatively prime, then this list modulo m, this list modulo m is the same. Now we know that b1, b2, all the way to bm are b phi m are relatively prime to 10. So if we prove that there are no recurring numbers in the list above, then we had finished the proof of this part. So we're going to get our two lucky guests and write them as BJ and BK. And then we have this, since we'll set that these two are recurring. And after that, we find that M can divide BJ minus BK times A after a bit of algorithm. Now, we know that N and M are relatively prime, as said above. So I must divide BJ minus BK, but same as Fermat's little theorem's proof, BJ minus BK must be smaller than M, since BJ and BK are both smaller than M. So BJ minus BK is 0, which means that they are the same term. So we have proven this part, and it will be very, very easy. I don't even need to clear all, actually. So we're going to multiply all of these terms together. B1A times, B1A times B2A, don't mind that ugly A, all the way to, as you know, B phi m A. And then it is congruent to B1 times B2 all the way to B phi m. And we'll set capital B to be B1 times B2 all the way to B phi m And we can also get out the a to be a to the 5nth power. Is actually, we won't write the times capital B, because we know that capital B is relatively prime to m. So we can just factor out the big B, the capital B, and we had finished the proof, just like we had in Fermat's-Little theorem. So that will be it for today, which is actually quite little. So that'll be it, and see you next time.